Okay, we are going to convolve x1 of t and x2 of t. I know it looks a bit daunting at first because they're both pulse functions and they both only have an amplitude of 1. It actually turns out being a little bit easy. So, as usual, we're going to start by flipping x2 of t to see what we're going to work with. And then so we can see that that's pretty simple as well. Still has an amplitude of 1. It's just flipped across the y-axis, and that is going to be the function that we're moving across x1 of t in order to do our convolution. Okay, so the first interval we need to consider is going to be between t is 0 and t is 2. And so let's assume that, t is a little bit less than 1. Then our convolution would look like that. And those two signals multiplied together are still going to have an amplitude of 1. And then, obviously, the integration is just the area under the curve, which would be what I shaded in right there. Or let's say that t equals 1, then we'd still have the same type of deal going on. And then the area would just be that little rectangle right there. So anyway, what we can see is if we call that little interval t, that the area under our curve or our convolution is just going to be t times 1 up until we get to t equals 2. So what we can see is that from 0 to 2, our convolution is just going to increase linearly. The next part that we need to consider is sort of this interval right here. What happens when t is greater than 2 and the signal that we're shifting kind of goes over this gap in between our pulses right here. So remember that what we saw earlier, that the signal we're shifting has a width of 3. I'm going to go ahead and draw that from 1 to 4. And so the parts that are going to be considered for our convolution are just going to be where the signals overlap, which is going to be from here to here. And what we can notice is that this is a rectangle with width 1 and height 1, and this is a rectangle of width 1 and height 1. And so the area under that curve is just going to be those two added together, which is still going to equal 2. So for t is greater than 2 up until t equals 4, we know that our convolution still equals 2. And so we can actually see that since this pulse is just a repeating pattern, that pattern is actually going to continue up until we hit something different. And that different point that I'm talking about is going to be over here at t equals 9. So once we get past t equals 9, we can kind of see that the signal is going to start decreasing, and I'll illustrate that by going ahead and drawing what it would look like at t equals 10. We can see at t equals 10, the only interlapping part is this section over here with, again, a width 1 and a height 1, meaning at t equals 10, our convolution is just going to equal 1. And then if we extend that over here until t equals 11, we can see it's the same thing. Again, the only interlapping part is right here, and that's again going to be width 1, height 1 up until t equals 11. Our convolution is still going to equal 1. Now once we get past t equals 11, we can see that we're going to have that same linear increase as t increases that we had earlier up until t equals 12, when our convolution is back up to equaling 2. And then, just like we had earlier, it's the same pulse function with the same width, and it's repeating with only this one width break in between as we had earlier, which is going to keep our convolution constant at 2 as it was before up until we get to t equals 19, and then we're going to decrease linearly, just as we did increase linearly in the beginning. And you can see the signal, sort of looks mirrored. The convolution sort of looks mirrored, which does make sense because our x1 of t is also, sort of a mirror of itself over t equals 9.